Hi guys, welcome to another Learn Electronics Repair video. I have something different today. This is a UPS, uninterruptible power supply, and this belongs to a subscriber who lives near to me, and I just happened to see him at the car boot sale a week ago, and he bought this. I think he paid €10 or something for it. So this has normally a battery in here. And I said to him, well, normally with these the battery fails, and he knew that, but he says basically he doesn't want to use this as a UPS, to back up a computer as people would normally do with them. He wants to use this with his solar panels. So he has solar panels connected to 12-volt batteries, and he wants to use this as an inverter. So not using the charging features of this thing, just literally to use it as an inverter. So I said, okay, let's have a look to see if that is actually even possible. I've never looked at one of these before, or for that matter, repaired an inverter before, assuming there's anything wrong with it. But we can see basically this is the mains power lead coming in, and that goes to what looks like a thermal trip on the back of here, or some sort of fuse trip, and then that, yes, that comes down this cable. So this has effectively the mains power coming in. So we can just disconnect that for a moment. If I can, yeah, there it goes. So that's the mains power coming in. Then we have, this is the power going out, mains power, and that goes to these are the sockets on the back of the unit. So this is the either battery backup power or the main power coming through, depending if it's just working as a pass-through or if it's working to supply power from the battery to the main. So that's that. This connection comes from the transformer, and then we have these red and blue ones also to the transformer. So it looks, this is just a guess, that they're using this transformer to step down the power to charge the battery, and they're also using this transformer to step up the power when it's running from battery. That seems to be the way this seems to work. I think I need to get this circuit board out, and then we can hopefully just figure out how this is connected up and see what we can do with it. Let's have a look at what we have here. So we can see in the casing that the mains power comes in here, and via the trip on the back this goes to the main PCB. So that's power coming in. We have these two, which is power going out to the main sockets on the back for the device that we want to run. Then we have a transformer with a center tapped primary, 3 connections, and a secondary. So that's what we have in there. On the back is just a little USB interface with a couple of opto isolators, but we don't want that, I don't think. So on the PCB, it's actually marked quite clearly, which is nice. So this says input IP, input N and L. So this is your live and neutral input on this connection. That's coming from the main power coming in. These are marked output, O/P must be output, live and neutral. So that's your 240 volt going out. This connector is the primary of the transformer, and although it has 4 pins on the connector, there's actually only 3 pins on the wire coming from the transformer. So that's that one. And then this one and this one is the low voltage coming from the secondary of the transformer, the red and blue wires, which you can see here. And they've actually marked on the board blue and red. So we have those, and the last thing is the two which go down to the battery, red and black. And if we have a look at this, we can see where the input comes in. So that goes here. And this comes across to a relay. And if you can see, it's marked. So we have a coil, which I guess is these two terminals. We have a switch, and we have the center pole of the switch here. So we can see that. So the power input, the live input, comes to this switch, and this relay can obviously switch it two different ways. And we can see from the switch that it goes to another relay here. So you can see from this contact goes to this one, at least switched into this position. Okay, and this has again two contacts. And if we look where these contacts are, one of them, this one, is clearly going down to this connector, and this is the primary to the transformer. So we can see that the relays in one direction to switch the main power coming into the primary. Okay, then we have the power out here, and again that connector is switched into another relay here. It's actually, yes, it goes from here to here, and if we look, there's actually a wire link there which goes to these contacts. So this contact must be able to switch the power output socket either to be directly on the power input when it's powered by mains, or when it's powered by the inverter. So that all sort of makes sense, and this must be the little microcontroller that's controlling that. So we can kind of see what we've got going on there. Now, the secondary of the transformer comes in here and here. And I would assume that when we're on mains power, that secondary is charging the battery. And when we're on backup power, the battery is running the inverter, which is sending the mains power back out. So it would seem to me that the transformer is either step down transformer when we want to charge the battery, or it's a step up transformer when we want to run the device at mains voltage. So we can see we have the connections, one coming in here and one coming in here, and I would guess that is probably going from the secondary of the transformer to a bridge rectifier. That would make sense. On here I see what I think are two chips. We'll look at them in a minute, and this looks like it's an opto-isolator to me. So it looks like an opto-isolator, but I don't see a bridge rectifier. So let's see on the other side of the board. So again, we have power coming in here and power coming in here, and although I don't see a bridge rectifier, this looks like 4 diodes here. Let's zoom down and let's have a look. Okay, so we have here clearly 4 diodes, D10, D16, D22 and D17 by the looks of it. 4 diodes. So if this is a bridge rectifier, we can fairly easily work that out, because one end of each pair of diodes will be connected together, providing the positive or negative output from the bridge rectifier. So let's have a look, see if we can find some ends of these connected together. Meter's working. No. Okay, yeah, so those two ends are connected together, and I think we can see there's a stripe on here and a stripe on here. So that's the negative end. So that looks like it's going to be the negative output from a bridge rectifier. And then we want the positive output. Not there, not there. Oh, there's a diode junction there, but not a connection. Where around did it go? There's a stripe there. The stripe's on opposite ends. So is it this end to this end? That would make sense. Yeah, I have it. So that's the positive output from the bridge rectifier, made of 4 individual diodes, and this is the negative output. So that's a bridge rectifier. There's then a capacitor near to here. There's a couple of capacitors. So I would assume then that is powering the logic circuit of this, the brain of it. This thing is being powered from there. So that's basically what we have, and this will control whether it's passing mains power directly through and charging the battery, or whether it's using the battery to provide mains power. So that just leaves the inverter. Well, that's obviously going to be on here because we have 4 large devices. They're all the same. Oh, yeah, looks like just get the focus of that kind onto that. In fact, just get my torch maybe, that will help us. I think they all look the same. Let's have a look. Yeah, IRL 8314, 8314. Yeah, these are all marked the same. So these are probably MOSFETs. And the 4 MOSFETs will be driving the inverter, which leaves us with 2 chips. So let's have a look to see what these are as well. This one, LM3241. So we can find a data sheet for that, LM3241. And this one is a UC something or other. I just have to get my magnifier, but I'm sure we can find the data sheet for that one. UC3843. Okay, let's have a quick look at these data sheets, and then I think we'll know everything we need to know about this circuit, basically, to see if we can modify this just to run from the battery as an inverter, and to see if it's actually faulty or not. I have found the data sheets for these chips. This one is actually an LM324L, not 3241, and it is a quad operational amplifier. Operational amplifiers in these sort of circuits are often used for current monitoring and voltage monitoring, over voltage, under voltage, and so on. So I suspect this chip is acting effectively as a sensor, kind of a supervisor for this circuit. Maybe it switches between sensing when there's an external power supply coming in, 240 volts, or when there's only battery power. And I would imagine it's involved with the sensing of that, and then the little microcontroller actually does the switching. So that's that chip. The other one, UC3843B, is basically a switch mode power supply type chip. You can see an example here of an offline flyback regulator. So this is actually a power supply. This is 5 volts, 12 volts. And I would imagine this chip is probably driving the inverter when we're running from battery power. So that all kind of makes sense with what we can see on the PCB so far. Quite likely then the opto isolator is connecting to this. So this chip is driving the inverter. This is monitoring the various voltages and current. And I would assume that this is switching this on or off, effectively being controlled on the low voltage side, and through the opto isolator switching this. So I think if we have a look under here, we should probably see that this opto isolator some way connects to the chip. I can't see a direct connection, but unless it's this side. Yeah, this sort of goes this way. I can't see a direct connection, but I'm pretty sure that's what that opto isolator is actually doing. It could just be detecting whether there's mains voltage or not, but I think it's more likely controlling this. So what can we do with this? Well, I think the first thing we should do is just check for any shorts on the output devices. If they're okay, I think we can just connect a battery to this with no mains supply and switch it on, and it should think it has a fully charged battery and start powering the inverter. So if we connect a load to the UPS, it should work. That's my first feeling about it, and I hope that's actually correct. So let's just check first to see if at least the MOSFETs, if there's no shorts here. I'm guessing they're MOSFETs. Could be transistors. So let's have a look. We're on diode mode. So we can see there's one MOSFET here. What have we got? Well, there's a diode junction there. And there's a diode junction there. So but the other way around. So it's not a bipolar transistor, or at least not a good one. So that's there. What the other one's doing? Diode junction there, is it the same here? Yeah, so an open, or well, pretty much open. They read the same. So again, third one, diode junction, and pretty much just reads, yeah, resistance. So these all at least read the same as each other, which I think is a good indication that they're okay. Yeah. So that all looks all right. So let's try connecting our bench power supply to the battery connections and see if we can get any mains voltage out of this. We need to have a think about the current draw. My bench power supply can only supply 5 amps. This fuse, which is obviously connecting to the battery, is a 40 amp fuse. If we look at the specification of this, now I may just have to adjust the focus for you one moment. This says the output, and I'm pretty much guessing this is based on battery, as 360 watts. So as a quick rule of thumb, to get 360 watts from a 12 volt battery, assuming 100% efficiency, which it probably wouldn't have, but it may be very efficient, 12 volts at 10 amps will give you 120 watts. So you're looking at 30 amps on the 12 volt to supply 360 watts on the main supply, assuming 100% efficiency. That kind of makes sense with the 40 amp fuse that we have. So if I use my power supply, which is 5 amp, I need to connect a load on here, which is 60 watts or less. If I use a little 5 volt wall wart power pack type thing and connect like an LED or something on the output, so effectively it wouldn't draw much load. If the inverter is working, the LED should light up. That's my theory. So let's have a look. Let's see if this thing actually works as an inverter. Okay, we're basically ready to go. This is just a laptop power supply, I think. And there's a 12 volt power supply, which has an LED on it, so it gives a little bit of load. I've not connected to anything at the moment, but the LED should come on if we have a main supply. We'll just take the bench power supply, and I'm going to set it to about 13 volts because a 12 volt car battery basically gets a bit more than 12 volts anyway when it's fully charged. So let's connect it to our UPS, which I think is switched off at the moment. We have an on-off switch. I think we can just stick these down here, probably the easiest way to do it. If you can see what I'm doing, so stick these spade terminals into here. That's this one, and this one I've set it to 5 amps, so it should give the full supply. I'd say the UPS is off at the moment, so I'm not expecting any particular amount of current to come out of it. Let's stick this in here. So yeah, that's it. So that's the power supply connected. So let's switch the UPS on and see what it actually does now. Well, it's making a blipping noise and saying some relays click, but then it went off. Oh, that's interesting. I thought it would come on. It's obviously made a sound. Let's try again. Yeah, so it's just powering up with a continuous bleep. Then I hear it clicking off. Do any of the LEDs on the front have it light up? Let's have a look. Just lift it up so you can see some LEDs on the front. They all light up and then go off. Okay. So it's not working just at the moment. I think we need to just check a few things. So first of all, is this power pack any good? And it does light up, so I'm sure the power supply is okay. So that's the first thing we've kind of eliminated. The next one then is maybe this actually wants a bit of a load before it'll actually run properly. So let's see if we can find something a little bit better to load this up with. Okay, so this should do. It's just a 22 watt 12 volt light bulb, so that's drawing best part of 2 amps from the power supply, which at 12 volts is 24 watts, which is well within the capability of my bench PSU to run the inverter. So that should be fine. So let's now connect back onto the inverter and let's see whether this works. Okay, so power into there, we've got the light bulb, we need the power into the power pack, of course. Go. And then we can switch on our bench power supply again. Okay, I've connected the light bulb onto the power supply. So let's have a look now. I have the input voltage set to 12.5. Switch on. Yeah, the green light just like flicks once and all the lights come on and it shuts down basically. It doesn't like something that is happening. Yeah, all 3 lights on. According to the user manual, it doesn't tell me anything useful, it just says there's a fault. I don't know if it's going to be very finicky about the input voltage. Let's just change the battery to 12 and let's go again and see what happens. Makes no difference, the same happens. I'll be honest, the guy who brought me this in took the battery out and he hasn't actually told me what battery voltage it is. I'm actually just assuming it's a 12 volt battery. Maybe that's where the problem lies. I'll ask him what voltage the battery is that comes out of this unit. Okay, he's bringing me the battery, he still has it. But bear in mind this UPS was faulty, I assume, when he found it at the second-hand market. And it may not necessarily be that the problem is the battery, although that's probably the most common cause. Let's have a look at the data sheet for the chip that's driving the inverter. Here is the data sheet. So we can see on our chip we have feedback input. This is to do with the effectively stabilizing the voltage output, current sense, oscillator timer. Output drives the gate of the power MOSFET. Okay, or in our case probably more than one. There's 4 on the back of this. We have a VCC on pin 7 and the reference output on pin 8. So that's basically what we have. So we can have a look at our chip in the meantime while I'm waiting for the battery to see A, do we have any VCC, and B, do we have any outputs. That's pin 7 and pin 6. So this is our chip, this one. I'm connecting the black meter lead to the negative terminal from the power supply coming in, because this is basically our ground terminal. That can go to there. And now let's have a look on the chip. So we'll go to pin 7 and let's see if this has any supply voltage VCC. Yes, it does, 12 volts, which then goes off when it switches off. Does it have any output? Is it driving the inverter? Let's see. We can use the meter to do this. If we go to Hertz mode, I'm sure we'll be able to see the frequency that it's driving. It's just picking up some 50 Hertz mains hum at the moment. So we're going to pin 6. Okay, we're on there. Well, let's just have a look to see. I don't see any output from the chip that's driving the inverter. Just check again to make sure I had a good connection. I'm pretty sure I do. I'm back on it again. Oh yeah, it changes to 0. So the inverter driver chip isn't running. Let's have a look at the data sheet to see if there's like an enable or anything else that would stop it from working. We can see we have an internal 5 volt reference in our chip, so we can check that. We know we have a supply of 12 volts. We can check if that's correct. And is there anything else that would cause this to shut down? Maybe the current sense. I don't see any enable pin. Let's have a look to see what we have. If I can just find the pin description for our chip. It may be further up actually. Just see, no, it's further down. Typical. Here we are. So VCC we have 12 volts. VREF on pin 8, we can check this. This should be 5 volts. If it's not, that would suggest there's a problem with the chip itself, or something is causing the chip not to run. But it should generate this reference voltage if it has power. We have no enable pin, as I can see. We have current sense. This is saying it's a current sense. Yes, PWM uses this information to terminate the output switch conduction. So if the current is too high, if it senses too much voltage here, it will shut down. So let's have a look to see if we can find information of what voltages we should have. I think it was further up actually. Yeah, in here somewhere. So what do we have? Well, we have the reference voltage we know should be 5 volts. Ours is the U38 4XB. It's a 4.3, I think. That's ours. So that should be 5 volts typically on the reference. We can check for that pin 8. Let's have a look at the current sense. So this is saying maximum current sense input threshold. So if the input voltage here is higher than the threshold amount, it will shut down. So that is saying 1 volt. So we should have 1 volt or less. In fact, we should have less than 1 volt on the current sense pin. So we can look at those two. We already know about VCC, but let's just see. We have 12 volts. Does it give us any information? Under voltage lockout. So for the 843 type, which is ours, it's saying the startup threshold. So the VCC needs to be 8.4 or more for it to start up. We have 12. And then once it's started up, once it's turned on, it needs to stay above 7.6. We had 12. So that seems okay. So we need to look then at the reference voltage and the current sense. And those are on pins 3 for current sense, less than 1 volt, and 5 volts on pin 8. First of all, pin 8, do we have a reference voltage coming out of the chip? Let's see what we have on here. So this should be 5 volts. We have a 5 volt reference, so that's good to see. And the other one on pin 3 is our chip sensing an overcurrent. So we go to pin 3, and let's have a look what we have here. It should be less than 1 volt. Oh, it seems to think it has an overcurrent. That's why it's not running. Let's just go on it again and see if that comes in straight away on the pin 3. Okay, we're on it. I'm just going to switch us off auto range, just into voltage range, just to be sure. Okay, we're on voltage range. 0 volts. Switch on. Oh, 4.4 volts. That's strange, the auto range didn't really read that correctly, did it? So very much this. Oh, 1.15, that's strange, I got 4. Let's go again, switch it off. 1.15. So this is why our inverter isn't running. It believes it has an overcurrent condition. The overcurrent will be sensing through a low value resistor somewhere. So we need to have another look at our PCB and see if we can figure out where the overcurrent connection is coming from. Just before I do that, I want to check one other thing, and that is that the ground pin of this chip, from which point we're referencing all of the voltages, is actually connecting to ground here, that we have the correct ground. So let's just see. And yes, we have a connection from there to ground. So we definitely have either an overcurrent or the controller thinks there's an overcurrent. Considering the power supply isn't running, I suspect some problem in the overcurrent sensing, or problem with one of these MOSFETs maybe. So let's have a look. Let's have a look then at our circuit and see if we can figure out where this current sense voltage comes from. The most obvious place is some low value resistors, where it is sensing the current by measuring the voltage drop across them. And the only things that look likely on here are these. So we have 2 high wattage resistors here, and they're in parallel. You can see that they're actually across each other, so in parallel. So I'm suspecting these are current sense resistors. They're normally quite large, and I don't see any other large resistors on here, surface mount ones for example. So I'm fairly sure these are the current sense resistors. They're also 0.1 ohm each, so that's 0.05 ohm with 2 in parallel, which makes a lot of sense. And lastly, we can see that one end of the resistors goes to the neutral end of output power. That also makes sense of where you would expect them to be. So I'm pretty sure these are the current sense resistors. Now we need to figure out if this connects to here. So let's have a look. So we know pin 3 is the current sense. So if we go on the... In fact, before we do that, let's just check these resistors are okay. Do we have open circuit current sense resistors? Because that would cause this sort of problem. Let me get the voltmeter where you can see it. Okay, maybe. Let's just switch it on. Let's just switch it on. There we go. And we can kind of do it like this. So we'll go to ohms range. But I'm suspecting they'll probably just read like a short. Let's have a look. So we have the two. In fact, it's easiest to do it from underneath, I would think. So we get from here. What have we got? Well, they read like 0, yeah, I think you can just see it. They read like 0, so they read like a short, which is what you expect them to do. But we can probably check them a little bit better than that. I'm going to use the low ohms meter and see if I can actually read them correctly. So here I have my low ohms meter. It's on 200 millivolt range, which is basically 0.2 of an ohm. Just zero it down. Yeah. So what are these reading? Oh yeah, it's like 0.05529. Yeah. So that they read okay. So I think we can say with confidence there's nothing wrong with our current sense resistors, assuming that's what they are. So they're reading good. We're on the 0.2 of an ohm range, and they were reading 0.05. Where's our current sensor connected to? Let's have a look. Let's put it onto diode mode, I think, and put the meter here where you can see it. Let's have a look to see what we've got. So we know pin 3 is the current sensor, and it has too much voltage on, so that's the third one there. We can go on this side, I think, and that's 1, 2, 3. I'm going to use the microscope, it's a little bit easier for me, and I'll also show you as well. Okay, so we can see. So we have pin 3 is, but this one pin 3. So this looks like it goes to a resistor here. Actually, it looks that way. No, not there. Let me just look at the microscope and we can see where this goes. So from here, pin 3. Oh yes, it does go there. 0 ohms. This is a 10k 01C. That's a 10k resistor, which we can just check actually just to make sure it's okay because it's in this part of the circuit. So ohms range. Okay, ohms range. So this is a 10k resistor. That means 10k. Now from this end, it looks like it goes. Oh yeah, it goes here. This is a transistor by the looks of it, or something similar. That it's probably base collector emitter if it's a transistor. So it looks like it goes to the emitter of here via 10k. So where's the other resistor go to? There's one here. Let's see, it goes to here. Is this in ground? Let me just get into the ground lead of the 12 volt where the battery goes to. Yeah, that's ground. So that makes sense. We've got a resistor divider between the emitter of that transistor and ground. Assume it's a transistor, that's diode mode. So if it's a transistor, this would be the base. Not sorry, this one. This would be the base. Yeah, we have a junction there. We have a junction there. 642. 621. So the one slightly higher is this one, 642. So that would be the emitter. So the collector must go to some power. Does it go to the 12 volts coming in? No. What's powering this chip? Ah, it goes there. Does that pin? Yeah. That's pin 8, which we know is reference. That's 5 volts. So we have a 5 volt supply to this transistor. The emitter goes to this feedback pin. So the base must control this. Where does that go to? Looks like it goes to another resistor. I'll put it back onto resistance range. But I think it looks like it goes here on this one. Okay, ohms range. Let's see where that actually goes. So that would be the base. So yeah, that goes to there. That's a 8.6k resistor. What it's reading? Oh, it says 9.1 something on it. Yeah, that sounds about right. It's a 9.1. It's reading 8.6. Another end of that resistor looks like. Does that go back to the collector here? Yeah, that's 5 volts onto the base as a pull-up resistor. So the other end goes. Does it go here somewhere? I see it coming somewhere in this direction. No, it doesn't go there. Oh, this goes to this one. Oh yeah, that's the pull-up. We know about the pull-up. So where's the other end of this go? Oh, that goes to this pin of the chip. And then this is the capacity to the ground. So we'll just get to the black lead of the input. You can't see me, but I'm on the black battery terminal. Yeah, that's ground. So I think I can see what we have here. What's on this pin 4? Let's go back to the data sheet and let's have a look to see what's actually on that pin. So here's the data sheet, and we can see that pin 4 is the capacitor. Oh, that's interesting. Look, we've got VREF, which we know is supplying our transistor, and we know it's connecting to here. And this is normally where you have a resistor that sets the frequency of the oscillator. Maybe they're using that to change the frequency. I'm not totally sure, but something like that's going on here, and then it's connected into the current sense. The circuit's a bit complicated, but that seems to be what we have here. But it seems that the current sense does not directly go to those current sense resistors. So let's have a look to see where they go to, and maybe that will give us some sort of clue better than what I can sort of see here as to where the current sense actually is. If we assume that these are the current sense resistors, I'm pretty sure they are, then one end goes to this resistor here, which we can see is a about 10k resistor, and from this end of the resistor, does it go to this chip? Yes, it goes to there, which is pin 7. No, sorry, pin 13. And this is an operational amplifier, and I suspect that's probably an input to the operational amplifier. Let's have a look. So we know the sense resistor connects to here on pin 13, and this is an operational amplifier, so it has 2 inputs and 1 output. And basically the way this works, we have a plus and a minus input. So if the plus input is higher than the minus input, then the output will go up towards V plus. That's the supply voltage, probably 12 volts on our board, or 5 volts. If the minus input is higher than the plus input, then it will go the other way. So the output will go down to ground. I would assume that pin 12, the positive input, will have a reference voltage on, and the pin 13 will be sensing the voltage on the current sensing resistor. So it will be comparing that with this. So let's have a look to see what we actually have on our board. First, I just want to check where the ground reference is. So I have my black meter probe in the wire coming from the bench power supply. And pin 11 is ground on our chip. So yeah, it's connected to there. So that's our ground reference. So we want to have a look on pin 13 and pin 12. Pin 12 should be some sort of voltage reference, probably 1 volt. So let's start our power supply up and let's see what we... Of course I've moved that because it's balanced on it. One moment. Things everywhere. Okay, so we'll start the power supply and let's see what we have on pin 12. We have 5 volts and then it shuts down and goes to low. Okay, so on pin 13. Five volts and then it shuts down. So you'd expect this, well, depending which one was slightly higher than the other one. And then it shuts down. It's a bit hard to say from those readings, but I'm fairly confident that is in actual fact monitoring the current. I think the way to tell would probably be to measure the voltage directly between pin 12 and 13 to see if we can see a difference in voltage. So I'll just hold the probes on. Let's see what we get. No difference, and then it shuts down. So the fact there's no difference, I'm not sure that the output should be high. So the fact there's no difference would suggest that there's no current flowing through the current sense resistor, which basically is because the thing isn't powering up. So I'm tempted to change this. I mean, I have no schematics on this, and the circuit is rather hard to trace. Between here and here appear to be a lot of transistors. I'm not sure how the circuit path goes. So I'm tempted to change this one and have a look to see what we have then. We have no difference between these two, and yet the voltage on here is switching. I'll just do it again. So the two pins 12 and 13. Okay, we're on there. We know the output switches, and yet nothing happens on the inputs. Is the power supply switching on and off? That wouldn't surprise me. We know where ground is. Let's go to ground and let's go the power supply, which is pin 4. What's on here? Pin 4. Let's see what we've got. A bit of a voltage. 12 volts. Off. Okay. So really the measurements I'm getting here are not that conclusive. At this point it's a good idea to try to get our feet on solid ground where we actually know a few things are okay. So given the fact this chip monitors the voltage drop against its current sense resistors, sure it does, and given the fact that on here we have too much voltage on the current sense input, and the fact it actually went to 4.4 on one occasion, but mostly it's just over like 1.15, kind of looks like an op amp that's acting a little bit strange. So let's change this first and then let's see if that makes any difference, although I'm not totally convinced it will, but we need to move forward some way. Okay, I've changed the op amp chip. I'm not totally convinced that this will make a difference, but it might do. So let's see what the thing does now. No, the same. Okay, and then trips out. Well, I came a long way round to this, but I've increased the voltage to 14.4. I can see on the battery It's a standby use 13.5 to 13.8, cycle 14.4 to 14.7. So on 14.4 volts, if we press the power, I now get the red light but not the others, with a continuous bleep, and it stays on. Let's go a little bit more. Let's take to 14.6. So this is between the two voltages, and let's see what it actually does now. The same. Do I still have this overcurrent condition? Let me just get the meter one moment. I'm back on pin 3, the current sense pin. Now it's acting a little bit differently. Let's have a look to see what we have here now. So we'll just switch on. No, we still have this effectively overcurrent symptom. So we know that our input is coming in here and the output is on pin 14. And this is connected to the current sense resistors. So it will be very interesting to see where this output actually goes to. Does it connect to our pulse width modulator chip? This is the output pin, and we can see it goes down a track here between the two pins, back along here, and this goes to a resistor here. And then it continues under this resistor, and it goes off down this way over here. Some more resistors, or possibly under. Well, it goes to here. This appears to go to the actual microcontroller, so it would seem that the current sensing on our board is being done by this op amp, and it's actually the microcontroller that's monitoring the current and switching things on and off depending on what it sees. It seems possible that the current sense pin on this chip is not being used for current sensing. We found the current sense resistors, we know they go to this op amp, and we know this sends a signal back to the microcontroller on the other side of the board. So this current sense pin might be, in our case, being used as an enable pin effectively, so that the microcontroller via the transistor circuitry we can see here can either put 1 volts or more on here to switch this off, or put less than 1 volts on here to switch this on. And to work out how that happens, we would have to trace back from here, reverse engineer the transistor circuitry, and see if we can find the way that that gets back to the microcontroller chip on the other side of the board. That's quite possible to do. It's a single-sided board. It shouldn't be difficult to do that. But before I go down that rabbit hole, I'm interested in a couple of things. Is the battery any good? If the battery is faulty, it would seem that this circuit board is probably okay. You would expect to have one fault. If the battery is faulty, and I can try to charge it from my bench power supply, maybe it will charge, maybe it won't. If it won't charge, I'm pretty sure this guy would have another battery that he intends to use with this from his solar panels, and I can ask him to bring that in and see if it works with that. The battery was no good. It wouldn't take any charge at all. I tried to charge it from my bench power supply and it would not take any current. So I had a little think about this, and I wondered if somehow the circuit is detecting the internal resistance of the battery, or in some other way detecting I have a battery fitted rather than my bench power supply supplying the voltage. Thinking on those lines, I asked my friend again, could he bring in another battery off his solar panel, and he's brought me this one. So I now have a battery which is charged up. We can just check it, one moment. Volts. So this battery has 11.69, which is a little bit lower than I was using 12 volts, so it's not fully charged. Again, I have the 12 volt light bulb on the power pack connecting from the mains output. So let's try it. Let's see how it behaves with the battery on. So again, it makes a bleep and it's working. So it would appear that there is some sensing component in this that can tell the difference between a battery and my bench power supply. This means, of course, that for the last hour we've been chasing a red herring. But having said that, I think I've certainly learned something, and you've probably learned something. First of all, we've learned something about how the circuit works, and secondly, we have learned that you cannot run a UPS off a bench power supply. Okay guys, so that's the conclusion to the video. It's now working. I'm very interested to know what you guys are going to say, so get your comments below. Somebody, can you explain why this would not work for my bench power supply? And while you're thinking of that, I will just say to you, ciao for now guys, and see you all soon on another Learn Electronics Repair video.